All right, so this assignment is going to help you practice all the different things that are tied into enthalpy or the delta H or the heat of reaction, all kinds of that stuff. So the first one, and probably one of the most difficult ones that we're going to do together, is the Hess's Law. So I'm going to do the first problem from this section, and from every section, I'll do either one or two problems. And then there will be one for you to do by yourself. And not everybody in the class has the same ones. So you need to try to do it yourself. Okay. So for the Hess's Law example, we all have the same number one problem where we're going to calculate the delta H for the reaction right here that produces the phosphorus pentachloride gas. So the idea is that we will know what the delta H is by the end of the problem. Okay, how do I approach these problems? Because I know people are just like, I just don't even know where to start. Okay, what I do is I look at the reactants and the products, and you find them in the bottom equations, and the step equations is what we call them. And you want to make sure two things. One, is it on the correct side of the arrow? So is it supposed to be a reactant? Is it supposed to be a product? And is it on the correct side? If it's not, then you flip the equation around so that you can do that. And you flip the sign of the delta H. Then, does it have the correct coefficient? So if it needs a 2 or it has a 2 and it needs a 1, then you would multiply or divide to get the coefficient correct. And you multiply and divide by everything in the equation and multiply and divide the delta H number. Okay. So for this reaction, the first thing I see is the 2P, and it needs to be on the reactant side, and it needs to have a coefficient of 2. So in the second equation, it has a coefficient of 2, and it's on the reactant side. So that means that we are not going to change that bottom equation at all, because the 2P is where it needs to be. Okay. So then now the next thing that we need to look at is 5Cl2. Now, when you have Cl2s or anything in multiple equations, then that gets a little tricky, because right now you can see that it's in the bottom equation with the 3 in front, and then the top equation with the 1 in front, and the top equation is on the product side. Since it is in multiple equations, on those chance instances, then I would say skip that one. If you get everything else figured out, those will work out in the end. Okay, so we're going to just skip by the Cl2 for now, but let's look at the 2PCl5. So that needs to be on a product side, and it needs to have a coefficient of 2. So right now, that is in this top equation, and it's on the wrong side. So that means that we need to flip it. And it does not have the coefficient of 2. So we also need to multiply by 2 so that we can get it to look like it needs to look like. Okay, so I like to cross them off and write them over again. So flipping things around, reactants and products switch. So it's going to be PCl3 plus Cl2, but we're multiplying by 2. So those each get a coefficient of 2. Those two in front, PCl5. Okay, and that, by doing that, that makes it so the 2PCl5 matches what we need in the equation. So that's good. But then we need to also change the number. So it was a positive 156.5 before. So we need to multiply that by 2. I forgot to do that. And we're going to make it negative. So when you multiply by 2 and make it negative, it will be 313, negative 313 kilojoules for that. Okay. So then now, once you look at both equations and you've done to them what you think you need to do to them, then last step is just combine your changed new reaction equations together, and that should match our original equation, and the delta H's should add to the right answer. So the 2P, we need to keep that. Now, the two PCl3s are going to cancel each other out. And the reason why is because they are on opposite sides of the arrow in each equation. So when you're on opposite sides, you subtract or you cancel out, okay? But then the CO2s, remember I said, hold on to that for later. So now that we have flipped that top equation, the 3Cl2 and the 2Cl2 are both on the reactant side of their equations. So since they're both on the same side, they add together to make a total. So 3 plus 2 is 5, which is what we needed. That I said we would get, it would work out, and I promised it would, and it did. So those add together, and then the product 2PCl5 is the only thing left on the right side of the arrow. So now, if we add together our negative 574 plus our negative 313, then that equals negative 887. Now, originally, since we had our 1 decimal place, let's keep our 1 decimal place here, and the label is kilojoules. Okay, so my hint for you is, because everybody has a different one, go ahead, step by step, look at each reactant, look at each product. And you're only going to change each equation once. So once you've looked at and decided what needs to be changed or what needs to stay the same about each of the step equations, then it should work out. And you need to add it together to make sure it works out and solve for that delta H. So if you would like to, maybe pause the video right now, and then you can move forward onto the next section. Or if you want to just do it all in one sitting, watching the video, that's fine. Okay, so I'm actually going to do 2 for the enthalpy example. So I didn't know what else to call these because all of these use dimensional analysis. Okay, I know on our assignment we had yesterday, students were like, what does that mean? They were asking me in the chat, what does that mean? Dimensional analysis means the parentheses. Okay, this is a great way to solve these, is that you're going to use the parentheses, set up the problem, and you're canceling out units. And once you set up so that the units cancel, and then you do the math, you get the right answer. Okay, so I want to do an example about what do you do if you have an equation and what do you do if you don't have an equation, because both of these types will be solved the same way. And we're not using the Q equals MCAT, we're using parentheses. Okay, so example 1 is an example where you do not have an equation. So we want to calculate how much heat in kilojoules is absorbed when 150 grams of liquid water is converted to gaseous water at 100 degrees Celsius. So like I said, we're not using Q equals MCAT, so that 100 degrees Celsius is just there to throw you off, or basically tell you like we're at the boiling point. Okay, what's important is the 150 grams, the fact that it's water, because that's going to be important, and then this delta H of vaporization, the molar heat of vaporization. Okay, so starting off these problems, first thing we do in our first parenthesis, put the number given from the problem over 1, the 150 grams. Okay, so we want to change the grams into kilojoules, but if you have grams, side note, then you're going to have 3 parentheses. If you start with moles, or if you're ending with moles, you just need 2 parentheses, but grams have to switch to moles before you go to kilojoules. Okay, so that's what our second parenthesis is going to be. We are going to set this up so that we cancel out grams and we're left with moles. So to cancel the grams, that means the grams will go in the denominator of the second parenthesis, and the numerator will be 1 mole. So the number that goes in is the fact that it's water, H2O. You will find the molar mass of water. So that's when you look up decimals from the periodic table, and 2 times 1.008 plus 15.999 gives you 18.015. So that is the molar mass of water. If you are unsure about that point, maybe come with like send me an email or something and ask me. Okay, so by doing that, then the grams are gone. And then last but not least, we want kilojoules. So again, we're gonna set up our third parenthesis so that we can cancel away moles and be left with KJ, with kilojoules, using the delta H gap value, okay? And so since the word absorbed is in here, we know we're gonna keep it positive. So we're gonna use that 40.7, and that's gonna go in the numerator with kilojoules, and 1 mole will go in the denominator so that the 1 mole will cancel each other out. All right, and that's it. Now we can solve. So you just take 150 divided by 18.015 and multiply by 40.7, and you'll get 338.88. I didn't round to sig figs first, so we could talk about that. When you round to sig figs, you could look at the original number or the delta H number. The original number, 150, is only 2 significant figures. So that means that we will round this to 340 grams. Okay, so that is an example. No, I should label that kilojoules. What am I doing? I am delirious because I'm sick and also it's late. There we go. Sorry, kilojoules. Okay, yeah. So that is an example of how to do it without an equation. Okay. Now let's talk about how to do it with an equation. So I'm also going to do example 2 with you. Okay. Or number 3, everybody's is different. So you're going to do that one on your own. So gasohol contains ethanol, and that formula is C2H6O. It's a liquid. When ethanol burns, that's ethanol. When ethanol burns, it reacts with oxygen gas to produce carbon dioxide and water gas. How much heat is released when 12.5 grams of ethanol burns? Okay, so this time, our original number that we're starting with is the 12.5 grams, which is important. So we're going to put that in our first parenthesis over 1, like we did in the first example for today. Okay. And then now the same process is going to be applied, because if we want to know heat, that means that we want to solve for the kilojoules. So at the end of the answer, hopefully I remember to label it as KJ. Okay. So we will divide by molar mass for our second parenthesis to cancel out grams. But this is where we have to be careful. So it's following along the same process so far as number 1, in that the molar mass will go in the denominator. But this is grams of ethanol, which the ethanol is the C2H6O, that thing right there. Okay, so this time we're not using 18.015. You have to take 2 times carbon plus 6 times hydrogen plus oxygen. And the number I got, which I hope is right, because again, I said I'm kind of tired, is 46.069. I think that's right. Okay. So then grams cancel. Okay. Now last parenthesis, because again, we're having 3 parentheses since we're starting with grams and going to kilojoules. We will use the delta H that we're given. Now, sometimes the delta H is at the end of the problem like this, which is great. It's nice and easy to spot. But sometimes the number is actually included in the equation. And so you have to go back to our notes and understand, what does it mean when it's on the reactant side or if it's on the product side, okay? If it's out by itself like this, this is just a lot easier to deal with. So what you do when it's an equation, you use the delta H number as needed. So here we want to multiply by the kilojoules, so we left with kilojoules. So that's going to go in the numerator. I'm going to keep the negative sign because the heat is being released. So I know it's got to be exothermic. But then on the bottom goes the coefficient in front of the chemical we're solving for. Okay, so since we're solving for the ethanol, whatever is in front of there, which happens to be a 1 this time, that will go with the mole. Because it's that much heat is released per that many moles of that substance. So if we were doing this for like the oxygen gas per se, then we would have to put a 3 and down there. But it's not about the oxygen gas, it's about the ethanol. So it's just a 1. Okay, and then the moles don't cancel out. So to solve it, 12.5 divided by 46.069 times negative 1368, and I got negative 371.182, and 12.5 grams is 368, so negative 371 kilojoules would be the correct answer. Okay, so you're going to solve for your number 3. That's different than other people's, and be careful about that positive or negative sign, depending on the type of heat of molar heat of solution that you have. But you're going to have 3 parentheses like we just did. Okay, so you can pause now and do that, or you can keep watching. All right, the last example that I have, and I don't have one for you to do because I didn't want to give you more than just one sheet of paper, because I feel like we're practicing this a lot, and hopefully you're getting enough practice. If not, I could help you find more. This is the last thing we did in the chapter, where you will write a balanced equation first. Then the idea is to find the heat of reaction. You take the products total minus the reactants total. Biggest thing I see, people subtract the wrong way. Everything else is great. And you also multiply by the coefficient of that thing. So let's write the equation. Okay, so I tell you the equation really, and then I also tell you the chemical formula. So I don't feel so mean about making you do this, especially since you're gonna have to write equations on the final exam. But we have solids calcium carbonate decomposing into calcium oxide and carbon dioxide gas. So the calcium carbonate is the CaCO3. And that's breaking down into the CaO and CO2. And this one happens to be balanced. You're welcome. This happens to also be one of the problems on the study guide. So if you would like to copy that down after you write it down here, that's great. Okay. So the next thing we need to do is we need to find totals for products and totals for reactants. So what I like to do is I like to write the number underneath the chemical that it belongs to, so I don't get confused later. Okay, and then since each of them have a 1, we don't have to really multiply by anything, which is nice. But adding the products together, so negative 635.1 plus a negative 393.5, you should get that number is negative 1028.6. Okay, so that's total products. So now to take our products minus reactants to find our standard heat of reaction, then we're actually going to take the negative 1028.6 minus a negative 1207. And so it's really adding that, right? On these, you always subtract unless you're subtracting a negative number. And so the answer is a positive 178.4. We're going to keep that 1 decimal place because each of our numbers had 1 decimal place, and we added to get our answer. And the label is just kilojoules. Okay, so the one that you can practice by yourself is the one on the study guide that's also like this. So I hope this helped you. Please try those other two problems on this worksheet that you need to do yourself if you didn't do that yet, and get that turned in today.